This video provides us with an introduction to finding inverse functions. If a function is one-to-one, then the function maps every x to one and only one y, and no two x values map to the same y value. This implies that there is a one-to-one correspondence between the input, the domain values, and the output, the range values, of a one-to-one function. So let's go back to this diagram that we've seen in a previous video. An example of a one-to-one function are people and their social security numbers. So our function f of x maps people to their social security numbers. People is the input or the domain values of our function f of x, and social security numbers is the range values of our function f of x. Because there's this one-to-one correspondence between people and their social security numbers, we could type in a person's name and find out what their social security number is, or we could type in somebody's social security number and figure out what their name was. This function that maps the output values back to the input values is called the inverse function. And that inverse function is denoted f inverse of x. It almost looks like a little exponent of -1. The context will tell us that this is not an exponent, but the notation of an inverse function. This function that maps social security numbers to people's names, social security numbers would then be the domain of the inverse of f, and names would be the range of the inverse of f. So it's interesting that people plays two different roles depending on which function you're looking at. People are the domain of f of x, but the range of f inverse. Similarly, social security numbers play two different roles depending on which function we're looking at. The range for f of x, but the domain for f inverse of x. So here's our formal definition of an inverse function. The function that maps the output back to the input of a function f is called the inverse function. We have three properties of inverse functions to discuss. The first one we've kind of already talked about, where people and social security numbers play two different roles depending on which function we're looking at. So our first property is that the domain of the inverse function is the same as the range of the original function, and the range of the inverse function is the domain of the original function. Our second property is that if you perform function composition with a function and its inverse, you'll always be left with x. Since function composition is not commutative, we have to look at that function composition both ways. F composed with f inverse and f inverse composed with f. They're both going to give us just x. Now, if we go back to our diagram, we'll see how this makes sense. If we start with some x values, people's names, if we first apply our function f, that gives us social security numbers, and then if we apply our inverse function, that takes us back to people's names, which is where we started, which were x values. Our third property is that the graphs of inverse functions are symmetric with respect to the line y equals x. And I have a diagram there to the right to show you that. Our dotted line is the line y equals x. We have one graph in blue, one graph in red. We can see that those two graphs are symmetric about the line y equals x. So let's consider the function g of x equals 2, 0, 4, 3, -5, -7. And we're asked to find g inverse. Well, the first thing you need to do is confirm that g is a one-to-one function. Since we're given a set of ordered pairs, we need to look and make sure that neither the x values nor the y values repeat. They don't. So this is a one-to-one function, and we should be able to find the inverse. We're going to use property number 1 of inverse functions to find g inverse. Our first property said that the domain of the inverse function is equal to the range of the original, and the range of the inverse function is equal to the domain of the original. Basically, the x and the y values just switch roles. So to get the inverse function, all we need to do is switch the x and y coordinate in each ordered pair. G inverse is the set of ordered pairs 0, 2, 3, 4, negative 7, 5, negative 5. In our next example, we're given the graph of f of x, and we want to graph f inverse of x. Now, property number 3 said that the graphs of inverse functions are symmetric with respect to the line y equals x. It can be really difficult to reflect a graph about a diagonal line. So instead, what I recommend is you start by finding several ordered pairs that belong to our original function f. Then we're going to interchange the x and the y values to obtain ordered pairs that belong to f inverse. This is what we did in the previous example. And then we'll plot those points and sketch the graph of f inverse through them. So let's start by finding some points that belong to f inverse. So here's one. Our first point that goes for f of x is going to be the ordered pair negative 2, 1. Next, I see we have a point here at 2, 3. And lastly, we have a point at 7, 4. To find f inverse, we're simply going to interchange our x and y values. That'll be 1, negative 2, 3, 2, and 4, 7. Let's plot these 3 points. And then we'll draw in our graph. You'll notice that our original f had an arrow on one end, so we need to be sure to have an arrow on the same end of our inverse function. That arrow was on the point 7, 4, so our arrow should be on the point 4, 7 when we draw in the inverse function. So there we have f inverse of x in blue. If I draw in the line y equals x, we can confirm that these two graphs are symmetric about the line y equals x. Next, we're going to use function composition to determine whether the given functions f and g are inverses of each other. We'll have to do function composition both ways, f composed with g and then g composed with f. If we get x both times, then these two functions are inverses of each other. So let's start with f composed with g. This is f of g of x. So that's going to be f of 3x plus 2. Everywhere we have an x and f, we're going to replace it with the quantity 3x plus 2. It'll be 3x plus 2 minus 2 over 3. We can just drop those parentheses since there's nothing in front of them. Combining like terms in the numerator, we get 3x over x. And lastly, we can simplify this fraction by canceling out the 3's, and we're left with just x. So we're good this direction. Now we need to check the other direction as well, since function composition is not commutative. Let's take a look at g composed with f. That's g of f of x. So that's going to be g of x minus 2 over 3. Everywhere we have an x in g, we're going to replace it with that fraction, x minus 2 over 3. It's going to be 3 times our fraction plus 2. When we multiply these fractions together, the 3's cancel out. That leaves us with x minus 2 plus 2. And combining our like terms, we're left with just x. So since f composed with g and g composed with f was equal to x, we know that f of x and g of x are inverses of each other.